and we talked about how we might discuss electric forklifts this week. We've heard that if you listen to the recordings. We talked about electric forklift, and an electric forklift running off a battery. The battery is recharged from grid power, for example, or it might be from your solar panels. And the question is, how long will the battery last? So I was going to discuss that during the tube, but I've actually downloaded a spec sheet of the Toyota electric forklift. And I'm going to upload that to Moodle, and that's going to be the basis of a little bit of homework between now and next week. And what it's going to do is going to synthesize a lot of the things that we discussed tonight. There's a few take-homes, or a few milestones I want to get to tonight. One is I want to go through a case study and the revision questions. I want to introduce my main take-home messages from topic 2. What was that, Scott? Hang on, let me just turn on the Q&A. Let's see if we can get some microphone happening here. So I think if you put up your hand, you'll be able to speak, but I just want you to explain or clarify your question there. If you do click the Ask a Question button, oh yes. Yes. I can't give you audio. The computer says no, so you'll have to type in your question. If you don't mind, or just a clarification of your question. Have you allowed microphone? You have to click on the audio button. Oh, okay. Yeah, so if you just take a little bit of time to type your question into the box there. So I'm just going to upload a presentation, a very small presentation, which I think really has a good overview. I think maybe of a lot of the topics in this subject, but particularly these opening couple. Yeah, so we'll be looking at all the energy it takes to run processes in the winery. We'll be looking at the amount of energy it takes to run pumps. Now, it doesn't matter what system you're in. If you're in a winery or in an aquaponics or an aquaculture setup, we'll be looking at how we work out how much energy is used for particular tasks. We'll be looking at what capabilities we'd need, or how we'd work out how much battery power we'd need to replicate that task in an off-grid fashion, so without using mains power. Or if we're deciding how much diesel it might take to run a generator to provide the power for particular appliances. So as we To start our progression through this, I'm just going to go through sort of a really important concept to start off. But first of all, I think the most important concept is our assessments. Well, I actually don't think they're the most important, but they are important in their own way. And this is due on, the first tutorial task is due on the 4th of August. It's actually due on the 8th of August. The 8th of August, which is designing a simple winery. And Robert, you can design a simple aquaponics centre or aquaculture centre, but it has to be, for the sake of the exercise, an indoor one. So here I've written for the winemaking guys and girls a basic 4 walls, a floor, and 2 tanks. So that quite obviously is applicable in an aquaculture fashion. Your tanks maybe just be a little bit wider and less high than a winery. That is due on the 8th of August. And this begins our fantastic journey through computer-assisted design. So a lot of subjects can actually be started this way. If we're discussing biology, biology can begin with this slide. When we're discussing engineering, what we're really discussing is energy transfer. We're discussing the transfer of something from a high concentration to a low concentration. And in terms of energy or electricity, we're talking about the transfer of electrons from high concentration to an area where there's a low concentration. And that's exactly how a battery works. A battery has one side which has got charge or a high concentration of electrons, and a side which has a low concentration of electrons. And what a battery does is allows us to form a bridge between the side which has a high concentration of electrons and that with a low concentration of electrons. And due to one of the basic laws of physics, substances will move from that area of high concentration to low concentration. Hence, electrons will move from the negative pole of the battery, where there's a high concentration of electrons, to the positive pole of battery, where there's a low concentration of electrons. And really, a battery doesn't actually run out when one side runs out of electrons. It actually runs out when there's no longer a difference in the number of electrons from one side to the other. Because electrons have to follow that gradient. In the case of water, we'll be talking about pumps. So if we have a tank which is 2 meters above the ground, and we open a valve, and that tank is full of wine or it's full of water, and we open a valve in the bottom of that tank, and that valve sits 2 meters above the ground, the water will move from that tank, which has got a high concentration of water, to an area on the ground which has a low concentration of water. And in fact, it's really not following a water gradient there, it's actually following an energy gradient. So really what that water has in the tank, it's got a high amount of potential energy, what we call potential energy. The ground, 2 meters below, has low potential energy. So the water is flowing along an energy gradient from high potential energy to low potential energy. Where does this potential energy come from? Well, to lift something from the floor up into the air, you have to counteract the force of gravity. And gravity is actually an accelerating force, accelerating at a known constant speed, 9.8 meters per second per second. So if we're lifting something from the ground up, we're actually counteracting the force of gravity. So when we're holding it up in the air, we're actually holding it against the force of energy. So there's lots of that substance now has heaps of inherent energy in itself because it's being held up against this downward force. So when we give it the opportunity, we can actually unleash this potential energy whereby water will move from the tank out of the valve onto the ground. So it's moving from high concentration to low concentration. In this case, it's moving along a gradient of potential energy. If that tank was empty, there's no water in it, it's not actually, the inside of the tank actually has no potential energy within it. We open that valve and nothing moves. Air won't move from an open tank to outside an open tank because there's no gradient, concentration of air gradient from one side of that tank to the other. Whereas if we blow up a balloon, that balloon has a lot of pressure in it because we're forcing a lot of air into a small space. So we have a pressure gradient. So air within a balloon's under high pressure, higher pressure than that air outside the balloon, which is at atmospheric pressure. So when we pop that balloon, air will move from inside the balloon to outside, following that pressure gradient. So again, things are just moving from high concentration to low concentration. So everything we talk about is really follows the same basic principle. When we plug our kettle into the wall, into the socket in the wall, and flip the switch, what we're then doing is allowing energy from the power station, where electrons are being generated, or really energy is being converted into electrons, or electrical energy. So we've got this power station which has got a really high concentration of electrons. We open up, we flick that switch, our kettle's got a really low concentration of electrons, so electrons will flow from that power station to the kettle. They'll follow an electrical gradient. High concentration of electrons to low concentration of electrons. So there's an electrical gradient, but it's following that high to low principle, just like everything. I like to think of things in that way because it's a sort of a unifying principle. And when I get confused about something, that's really how I bring it back so that I can remember it. And I really do. It's not like physics and engineering isn't something that comes to me naturally. It's not how my brain operates. So I need to convert it into terms that work for me. And so sometimes I'll be discussing things in the way that I understand them. But it might not be the way your brain operates. So this is one of those subjects where there's a lot of materials out there. You know, Khan Academy will have their own explanation of electronics, pumps. And so by all means, if you need to fill in some gaps with the way I've explained things, please go out there and just hear different ways of explaining some of these concepts. Because they'll come to you when your brain finds the way to understand them. So in our first topic, and feel free to click on that introduction to engineering, we discuss some really important concepts. The first one is energy. And energy really is the ability to do work. And what work is, when you break it down, the definition of work is the application of force over time. Force over distance. So work equals applying a force over distance. So if we push something or we carry something, over a certain distance, we know when we start aspiring, we're carrying out work. I stupidly ran the half marathon on Sunday. and I finished as a sweaty, disgusting mess, and I knew that I'd done work. I'd applied force over distance. What was the force? Thank you. What was the force that I was applying? What was this? What is this force? Force is measured in newtons. And this can be a really quite confusing concept. And it's a good point to pause actually. A lot of these notes provide a lot of background on these theoretical concepts, not all of which you need to understand. In fact, really, not a lot of the theoretical concepts you'll need to understand to get 100% in the subject. For example, you don't need to fully understand the concept of acceleration. You don't have to fully understand alternating current. You just have to know the key principles, the basics behind them, such that you can apply them in your field. So let's get an example here. There we go. Force. What's a Newton measuring? Newton is measuring the movement of a mass over movement of a mass at a certain acceleration. So force is a unit of measure which tells us how much effort is being applied to accelerate something, make something increase in speed. We normally measure acceleration in meters per second. So how many extra meters per second of speed do we increase per second? That's acceleration. So if we're just moving at 100 meters per second, that's our speed. If we're increasing the speed, it's how many meters per second of speed are we increasing per unit time, in this case, seconds. That's our acceleration. To get force, it's how much weight or how much mass are we actually accelerating. That is force. So force equals mass times acceleration. And so often it's what the really confusing concept here is, and you don't need to fully get across this straight away to answer the problems, the questions that we'll have coming up. But by looking at the theoretical basis to it, it will give us an entree into how we do calculate things, like the energy required for basic tasks. So I might go, Scott, can you carry this box across the room? Can you carry that box at a steady speed of 1 meter per second? It's like, oh, okay. I did that for you, Alistair, and I'm actually a little bit puffed at the end. So I'm pretty sure there was some force involved. I had to actually make some effort here. And that's true, you are, because even though you're moving at constant speed, you're actually having to accelerate against gravity and against friction. So when we're walking across a room, we're actually having to move against maybe wind, move against just the density of air. So we're actually having to accelerate against that friction. It just so happens that if you're moving at constant speed, the friction of the air is counteracting your acceleration. So you're actually still applying a force. You're still accelerating mass. Because if you weren't accelerating the mass, that friction would actually slow you down and stop you. So you're actually technically constantly accelerating when you're walking, even if you're moving at the same pace. So that's the friction. It's actually moving against the density of the air. The other thing we're having to apply force against is that of the downward push of gravity. So gravity is constantly pushing down upon us, and that is an agent that needs to be counteracted with acceleration. We have to push up at the same speed that gravity is pushing us down. The net acceleration is zero. We're not actually increasing in speed, but we are actually applying a force up and gravity is applying a force down. It just so happens that they meet in the middle. If gravity tripled, we may be crushed into the floor. That's because our acceleration up is no longer counteracting. And gravity is not a gradient because gravity is a constant in our atmosphere. Once you move out of the atmosphere where gravity is constant, at that point gravity becomes a gradient because the further you move away from the gravitational pull, less gravity is. Therefore, when we go into a zero gravity environment, you can carry a box really easily because you're not having to accelerate against that force anymore. And it's really easy to run really quickly along the ground because you're not having to accelerate against the friction of the air that you're in. The density of the air decreases, like there is a gradient of friction from the air. Not a gradient of gravity in the atmosphere, but there is a gravity in pressure. So if we go up a mountain, the atmospheric pressure is lower. The density of the air is lower. That's why people do high altitude training, because they're running against a lower pressure. And therefore, when people break records at high elevation, they get a asterisk next to it because it's easier to break speed records at high elevation. Incline or decline. When we're going in decline, the activity of gravity is then acting more on our lateral progression. So let's get a blank slide up here. That's the ground. And it's going to hit change the color. This is us. So when we're walking in this direction, say here, we've got a number of forces accelerating against us. So we have the friction of movement through the air, and we have the force of gravity acting down upon us. So when we're walking laterally, we're only acting against that friction from the air, and we only have to counteract gravity by standing upright. However, when we're walking up a hill, all of a sudden we have to counteract gravity to a certain degree in our forward movement as well. Therefore, it's harder. On the other hand, when we're moving down, gravity is actually partially assisting us on the decline. So it requires less force to counteract the other agents acting against us. That's why it's easier to accelerate, so actually overcome the forces acting against us when we're going down a hill compared to going up a hill. We have to accelerate even more to speed up a hill because we're having to counteract more of the force of gravity against us. So that can be a strange concept at first, this concept of force, because it's like, I don't accelerate everywhere I go, but all these calculations require me to accelerate before I can actually calculate, the amount of joules it takes to do a task. Well, it's because we are actually accelerating. It's just we're accelerating against other forces, opposite forces, which makes us not actually speed up. So we've got this concept of force, which is mass times acceleration. But most often we talk about effort that we do in terms of work. And work is when we start including a spatial component to it. So work equals mass times acceleration times distance. So it's a certain amount of a thing accelerating at a certain speed, velocity, over a certain distance. And work is when we start getting into terms which we can then apply to. Hi Hannah, how are you going? Welcome on board. How are you? Can you hear me joining on? Just type something in there, Hannah, if you can hear me. I'll type something in. Oh, you're typing now. Fantastic. Well, I'm just talking about work. You may have just come from work. But work in an engineering sense is mass times acceleration times distance. So I'm just going through some take-home messages from topic 1. So this is where we start getting into units and concepts which really help us start modelling things in our winery or whatever industrial setting we're discussing. Because work is often discussed in terms of joules. And I think it's the first page of the notes, it gives us that definition of a joule, which is 1 Newton of force. So 1 Newton acting on 1 kilogram over 1 meter, and that equals 1 joule. Oops, 1 joule. So when we've got 10 joules, when we've done 10 joules worth of work, we could have moved 1 kilogram over 1 meter at 10 newtons of force. So we're accelerating it hard. Or we could be applying 1 Newton of force to 10 kilograms over 1 meter, or 1 Newton of force to 1 kilogram over 10 meters. All of those require 10 joules of work. So here I have a question. And again, this is in great terms, Robert, however, is equally applicable to bags of sea salt that might be going in your tanks or whatever. But this is the case study that I'm posing a question to you. You've received a pallet. Yes. Well, it's all just about using these concepts, Robert. So they're equally applicable. So this one here has got grapes, but equally it could be fish or fish feed or whatever. So you can put it in whatever terms that you like, but it's all just looking at concepts of engineering. Yeah. So we received a pallet, and the pallet is 10 centimetres off the ground. On this pallet, we have 25 boxes. Each box is 30 centimetres high. Each contains 20 kilograms of stuff. This stuff has to be moved into this hopper here, which will then eject it into the top here of this crusher destemmer. So this could equally be creating fish feed. And that could be, on the end here, we could have a mill. So we've got two options. So what we need to do is have to get the boxes here, the contents of these boxes, into this hopper. Or this mill, into this little hopper here. This hopper here sits 1.4 meters above the ground. We have two options for doing this. Option one, manually tip the boxes from the pallet into the bin here. This is the bin. Then we forklift this bin into the receival hopper here. This receival hopper operates at 1.6 kilowatts. This receival hopper then takes 5 minutes to transfer the grapes into the crusher, or it could be the fish food into the mill. So we've got a receival hopper running at 1.5 kilowatts. And so we haven't talked about kilowatts tonight, but we're going to discuss those after this. So this hopper here takes 5 minutes using 1.5 kilowatts, running at 1.5 kilowatts, to transfer the contents of these boxes into this crusher here. Option two, so that's a simple one. So what we're doing is we're emptying the boxes into the bin manually by hand, and then forklifting the bin up into here. So probably my arrow, and I'm going to have a horrible amount. We'll talk about that. So bins manually placed into the contents of the boxes, manually put into the bins. The bin is then forklifted up into this hopper here. The hopper runs for 5 minutes and empties the contents into this machine here. Option two, we go, well, let's not bother all this stuff around of emptying the boxes into this bin here, then forklifting up into the hopper, and then the hopper into the crusher destemmer. What about we just manually empty the boxes into the crusher? The question is, which option requires more overall work and by how much? Which option requires more human work and by how many calories? 1 joule equals 0.24 calories. So this is the problem which we have in front of us. So what do we need to know to get to the answer to this question? Let's start with option one. How much energy will it take to remove the contents of the boxes and get them into the bin? What sort of information do we need for this? Can anyone give me any suggestions about what information we'd need to work out how much energy it would require to get the contents of these boxes and empty them manually into this bin. Yep, so we need to know the weight of the boxes, that's right. Yeah, so as we move the boxes from top to down, we will gradually be lowering the height of where the boxes are in relation to the bin. So let's imagine, let's talk about this top. Yep. Yep. The only problem there is, Hannah, which is a very good question, a very good point, is we don't know the length of these boxes. So let's just assume the only work we need to carry out is getting the vertical distance that's involved. So either getting the contents from above into the bin or below into the bin. So what we know, that these boxes are 20 kilos each, and we know there's 25 of them, and we know their height above the ground. So let's start with this top one. How high is that box off the ground? And let's say, how high is the bottom of that box above the ground? No, the very top one. The very top one. The top box. So the pallet itself, this pallet at the bottom is 10 centimeters. And then each box above is 30 centimeters high. So the bottom of the first row, yep. No. So the pallet itself is 10 centimeters, and then each box is 30 centimeters. So the first box is sitting 10 centimeters above the ground. Then the second layer would be 10 plus 30 centimeters above the ground. So let's say layer 1 equals 10 centimeters because it's just the pallet, height of the pallet above the ground. Layer 2 equals 10 plus 30 centimeters above the ground. Layer 3 equals height of a pallet plus a box plus another box. So it'd be 70 centimeters above the ground. Yep. Layer 4 equals 10 plus 30 plus 30 plus 30. Now that would be 21 meters. So we've got 10 centimeters of the pallet, and then box 1, 2, 3, 4, 5, 6. So this very top box has 6 boxes here, 6 boxes and a pallet below it. So it'd be 6 times 30 plus 10, which is 190 centimeters. So that box sits 190 centimeters above ground. So the question is, would it require any work? So that's force times mass times acceleration, force times distance, or mass times acceleration times distance. Oh, fair enough. Work, so remind us of work equals acceleration times the mass times the distance. So let's imagine we just want to lift a box from the floor 0 centimeters, and we want to lift it into that bin. And I've covered it with yellow paint, but that bin sits 1 meter above the ground. How much work is required to get that box into that bin if we're picking up off the ground? So the distance, so remember it's A times M times D. We need all of these. D equals 1 meter. The distance is 1 meter. So D equals 1. Mass is measured in kilograms. And in this case, we know the boxes are 20 kilograms. So M equals 20, D equals 1. The only one we need now is A. A is acceleration. So let's imagine we're lifting this box at a constant speed. We're not accelerating it as we go up. We're lifting it at a nice controlled constant speed up. If we're not accelerating it, there's no net acceleration in that box. We're just lifting it at a constant speed. That means the only force we're counteracting is that of gravity. And gravity is 9.8 meters per second per second. Therefore, the acceleration, if we're lifting a box at constant speed, we're actually accelerating it at the same rate as gravity is pushing down. So A is 9.8 because acceleration is measured in meters per second per second. The speed that things increase per second. So now we have everything we need to calculate work. Work equals the mass in kilograms, 20, times the height in meters, which is 1, times gravity, which is 9.8. So it equals 20 times 9.8, which equals 196. What is the units of work? The units of work are either in Newton meters or joules. So we would actually have to use 196 joules of energy. That's right. We'd have to use 196 joules of energy to lift that box at constant speed up to the height of that bin. So that's all pretty easy to work out. We just need that formula. Mass times acceleration times distance. Alright, so let's go layer by layer. Let's start at layer 1. Layer 1 is 10 centimeters above the ground because it's on a pallet. Yeah, so how do you calculate calories there? So 1 calorie equals 4.184 joules. So if we divide 196 by 4.186, that will give us the number of calories. And you're quite right, 47.04. Well done. Well, it looked correct anyway. Top work. So we'll go back. So layer 1 is 10 centimeters above the ground. Therefore, if we were lifting a box from the pallet into the bin, which lies 1 meter above the ground, we have to lift it 0.9 meters. So how much work would that take? 0.9 times the acceleration we need, which is 9.8 meters per second, by the mass, which is 20 kilograms. So I get my calculator out. $176.4 joules. So by having the box on the pallet, we've actually saved ourselves about 20 joules of energy. Yep. So how many joules would it take to lift the 4? 176.4 times 4, which is 705.4 joules of energy. Alright, so that's layer 1 would take 705.4 joules to get into the bin. Layer 2, okay, so layer 2 actually sits, 10 plus 30 centimeters above the ground, 40 centimeters. The bin, which we're entering the boxes into, is 100 centimeters above the ground. So there's a 60 centimeter or 0.6 meter difference in height between the bottom of the second layer and the bin. So to pick up that box and get it into that bin, we need to lift it 0.6 meters. So how much work would that take? 0.6 times 9.8 times 20. 0.6 meters times 9.8 meters per second, that's the acceleration we'd need to counteract of gravity, times the weight of the box, or the mass of the box, which is 20 kilos. 0.6 times 9.8 times 20 equals 117.6 joules. So it's a lot easier only lifting them 60 centimeters compared to 90 centimeters. How much would 4 take? 470 joules. Times 4, because there's 4 boxes in each layer that we need to lift to get into the box, into the bin. Then layer 3, what if we need to move the 4 boxes from layer 3 into the bin? Layer 3 is 10 centimeters of the pallet, plus 30 centimeters of layer 1, plus 30 centimeters of layer 2, which equals 60 centimeters or 0.7 meters. So that's only 0.3 meters below the bin. So now the work required equals 0.3 times 9.8 times 20, which equals 0.3 times 9.8 times 20, 58.8 joules per box, or times 4, 235.2 joules for all of them. All right, so this is where it starts getting interesting. So to lift those boxes, it was 235.2 joules for layer 3. $470.4 for layer 2, and layer 1 was 705.4. So what's that about? 1300 joules or 1.3 kilojoules. I'll just add that up properly. 235.2 plus 470.4 plus 705.4. 1411 joules of energy to lift the bottom 3 layers into the bin, or empty them into the bin. Alright, so we've expended 1.4 joules, that we would have to use 1.4 joule, 1,411 joules to empty those boxes into the bin. But what about these layers above? So layer 4 equals 10 centimeters plus 30 plus 30 plus 30, because there's 3 layers below it, which equals 1 meter. So it's actually the same height as the bin. So there's 0 meters difference between where these boxes are and the height of the bin. So the work required would be 0 meters times the acceleration of gravity, 9.8, times the mass of the box, 20 kilos, which equals 0 joules, because anything multiplied by 0 equals 0. So technically it actually take no work at all to empty those bins those boxes into that bin. Well, as Hannah quite rightly pointed out, we would have to move them from one side of the pallet to the other, which would require work because we're moving them horizontally. But here, just for the sake of this exercise, we're just imagining we're just tipping them in. So it's actually 0 joules to get layer 4 in. What about layer 5? So layer 5 equals 10 centimeters of pallet plus 30 plus 30 plus 30 plus 30, which equals 1.3 meters. So layer 5 is actually 1.3 meters above the ground. The bin is 1 meter. So it's actually negative 0.3 meters. It's actually not below the bin at all. So how much work do we need? It's actually negative 0.3 times 9.8 times 20. So we would actually get energy from the movement of the bin from above, movement of the boxes from above the bin into the bin. That's because we have gravity, the acceleration of gravity acting on the grapes in these boxes. So that is what we call momentum. So we're actually releasing the potential energy of these grapes when we're pouring them from above the bin into the bin. We're getting what's called kinetic energy, the energy of movement. And that's a really important energy. That's how we drive turbines. For example, we move water through like a propeller, and that drives a turbine, which creates energy. That's utilizing, there we go. We're actually generating 235.2 joules of energy. And so if that's a dam, we're actually able to convert that kinetic energy into electricity when we use the movement of water to turn a turbine. That's how we make electricity. So in terms of work, it actually doesn't require any work at all to lift the bins at the same level, the boxes at the same level or above the bin. So the overall work that is required for entering these boxes into the bin is 1411 joules. Yeah, spot on. So the higher the boxes are above the bin, the more kinetic energy we would produce from dropping them into the bin. It's the same with dams. If you have water higher up above the turbine, you will actually generate more kinetic energy from that turbine. You will produce more joules of energy. So the best dams are when we've got a really, really high lake and a really, really low turbine, and water's moving from that really high level to a really low level. We can generate a lot of electricity. All right, so we've used 411 joules. Yeah, that's right. Technically speaking, in this theoretical example, it would only take 1411 joules of work, of energy, to empty those boxes into the bin. Next, we need to lift the bin into the hopper. How much energy does that take? Well, it says we have to lift it 3.2 meters. So that means the work to get that bin into the hopper would be 3.2 meters times the acceleration of gravity, 9.8, times the total weight of grape in the boxes, in the bin, which is 25 times 20. Because we've entered 25 boxes into that bin. So that equals 500. So it would be 3.2 meters times 9.8 meters per second times 500, which is 15,680 joules. So that's like a lot of energy, 15.68 joules of energy, kilojoules, or 15,680 joules to lift that big weight up that big height into that hopper. That's why we need to get a forklift to do it, because that's a lot of energy required. It's a lot of force required to lift that bin. And that's not the amount of force which a human is able to apply. No human on Earth is able to apply 500 kilos and lift it 3.2 meters into a hopper. That's why we require a machine to do it. Oh, g'day Guy, welcome. It's great to have you on. So then you can, it brings up a point. Now you can think about theoretical tasks and go, okay, is it possible for a human to undertake that work, or do I require a machine to do it? Yeah, no one is tall enough either. Okay, Guy, welcome. This whole shoot's being recorded, so you'll be able to listen in to what you've missed. Now, hang on, I've just got to plug my laptop in, 1 second. Yeah, so it's really, all of a sudden, armed with a little bit of understanding about, gravity, what work is, you can actually start modeling different tasks. That's right, mate. Yeah, it's all been recorded, and I'll post up this case study. In fact, I'll open it now, and so you'll be able to have a look at that case study too. Not case study, it's case study 1, but you'll be able to look at the case study and go through it in your own time. But we're going to finish it off here. In fact, no, it's already there. It's already there. All right, so we calculated the number of joules required to. Oh, sorry, it's a 6:30 start. Sorry, Hannah. Sorry, everybody. Is 6:30 all right? 6:30 too early? I could make it 7. I don't know. In fact, 7 probably works better for me. Yeah, yeah, you're exactly right. So straight away, we can pretty work out that, yeah, cool, let's go for 7. So I'll post that up on Moodle and go for 7 o'clock. And my apologies for that if I've confused you there. So I think we can pretty much see straight away that option 2 is going to be a lot easier for us. I mean, in terms of work involved. However, we've got to think about time, and we've got to think about the cost of that energy. Like, is the cost of 14,000 joules of LPG? Yeah, that's right. It's wages, and also LPG, those joules of energy from a human requires food, and a human can only expend a finite amount of joules in a day. So do you want a human to expend 1,411 joules on this task? Or do you want to get our forklift to do however many joules it was to lift that bin for us? So these are the things we can start modelling now as engineers. Time is money. We can start modelling it because we're engineers now. We can start modelling these tasks and go, what's more efficient? I know this one requires less joules, but not all joules are joules. I can't believe I just said that. So I think we can see now that it's actually more efficient in terms of actual overall work just to empty the boxes straight into the crusher destemmer here. But the next part of option 2, yeah, that's right. But I mean, ergonomically speaking, yes, but in theoretical work, if we're talking about theoretical work, that's force over distance, then the height doesn't matter if you can reach it. Theoretically, it's just a certain amount of work, but ergonomically, we get strain. So we're talking about strain. So if you have to lift an object awkwardly, you're not necessarily applying more work. You're actually inducing strain on your body, and strain is a different engineering concept of tension and compression. So we will go over strain when we're talking about fencing and tension later on in the subject, in the course. But really good question, Hannah. So let's have a look at this. In option 1, we have this little thing here that says the forklift the bin into a receival hopper. Yes, compensation is expensive. Into the receival hopper running at 1.5 kilowatts. Yeah. Yes. What is a kilowatt? Or what is a watt? And the watt comes up in topic 2. We really start discussing watts. The watts is, so we've talked about, we've talked about force. We've talked about work, which is force over distance. Yeah, that's right, it's a measurement of electricity. And then a watt is when we start talking about something called power. And power is force over time, or really work over time. Right, so we're gradually building up towards more practical measures of energy here. So we've got force, that's what we're exerting to accelerate a mass. And then work is when we're forcing or accelerating a mass over distance. And then when we talk about power, we're applying work So force over a distance over time. And we talk about power, we often talk about watts. And that brings me to, and there's a big discussion in the notes about this, and I've got topic 2 and topic 3 open now. But what is a watt? A watt equals volts times amps. Now, who here is comfortable with the concept of volts and amps, or can explain to me the concept of a volt and concept of an amp? It can be a very tricky concept to get our head around at first. The notes go into great detail to provide examples explaining volts and amps, but I'm going to introduce it here, which will lead us into topic 2 and topic 3. Topic 1 also has a revision quiz, and I will post up the revision quiz for topic 2 and topic 3 as well. Right, so let's talk now about power. And when we talk about power, we often talk about electricity. So let's start talking about electricity here, because this receiver hopper is using 1.5 kilowatts, or it's rated at 1.5 kilowatts of electricity. So volts equals current times resistance. So what is this concept? So a volt, 1 volt equals 1 amp of current flowing across 1 ohm of resistance. So 1 volt equals 1 amp over 1 ohm of resistance. So what's all this on about? What am I talking about here? So this is where we're talking about potential energy again. What a volt is potential electrical energy. And what volts really is a measure of is if we have a lot of if we have a lot of electrons, let's say in a battery, and we connect that battery to the conductor, to something which has no electrons in it. We've got a big gradient between the high concentration of electrons and the low concentration of electrons. And that will force those electrons to move from the high concentration to the low concentration. The speed at which those electrons move from the battery to its destination, from the high concentration of electrons to the low concentration of electrons, is referred to as the current. And current is measured in coulombs per second. And a coulomb is a certain number, is a set number of electrons, which I can't remember off the top of my head to be honest, passing a point per second. So let's get this into terms you understand. We know what electrons are. They're those little negatively charged particles. Current is the speed of these electrons, the flow rate. How many of these electrons are passing through a particular point along a conductor, let's say a wire, per second. The resistance is the friction acting on these electrons. So let's say we have a box here. That box is absolutely full of electrons, here just designated as negative signs. And over here we have a box. This is our kettle, and it's got very, very few. It's got 1. They're far apart, so there's no way that electrons can move from box 1 to box 2. To get from box 1 to box 2, they have to pass through, they have to conduct along a conduit. They have to follow something to get from one box to the other. It's just like if we're at our house and we have to get to work, we have to go along a road. If there wasn't a road, we wouldn't be able to get to work. Electrons require that conductor, that road, to get from one point to the other. So let's say we connect box 1 full of electrons to box 2. Now we're allowing our electrons to follow this concentration gradient. The speed at which the electrons move from box 1 to box 2 is the current. Let's call it the flow rate of electrons equals the current. It's just like a river. If a river is running really slowly, you have a small amount of water flowing past a point in space. You've got a low flow rate, you've got low current. If you've got a lot of water moving past a point in space, you've got a strong current. The water's moving quicker. What helps things move at a higher flow rate? It's less resistance. So if we reduce the resistance in our conductor, that allows more electrons to move at a given speed. So we can pass more electrons through this conductor over the same amount of time if we reduce the friction acting on them. And we call this friction acting on the electrons the resistance. So what's one way we can have resistance acting on current? Well, or how do we reduce the resistance? We could increase the size of the conductor. So if you've got a wider conductor, you actually allow more current, more electrons to pass through it over a given amount of time. So you increase your current. If you make the conductor narrower, less electrons can move through over a given amount of time. It's just like if you have a pipe with water, if you've got a narrow pipe, only a small amount of water is able to flow through it. If you've got a wide pipe, more water can pass through over a given amount of time. That's one way we can increase or decrease the resistance, by increasing the size or width of the conductor. Another way we can change the resistance, so how easy it is for our electrons and what rate our electrons can move through this conductor, is by changing the material. Let's think about our stream again. If we fill our stream full of reeds, they're causing friction on the water and they make it slow down. And so less water can move through a point in space over a given amount of time. If we increase the width of that river but keep the reeds there, we'll be able to, the water will still be moving at the same pace, but more electrons can move through a given point over a given amount of time. So we're increasing the current. If we increase the size of the river and remove the reeds, we're going to allow even more electrons to move through over a given amount of time, which will increase the current. This is exactly why you buy expensive speaker cable, and it's really thick. It allows more electrons to flow through it over a given amount of time. That allows more current to be sent from your amplifier to your speakers. We increase the size of the pipe, we allow more water to flow through that pipe over a given amount of time. So current and resistance are inextricably linked. One of the difficulties with understanding electricity is we try and think about things as mutually exclusive things. One thing times another thing gives us one thing. Well, actually, they're linked together. Resistance is linked to current. Current is linked to resistance. So voltage is the overall potential of electricity to move. So if we increase the current, we're increasing the potential for electrons to move. If we decrease the resistance, we're increasing the potential for electrons to move. And vice versa. If we lower the current, we're reducing the potential for electrons to move. So what watts actually are is the volts, so the potential amount of electrons times the current. So what does that mean? So it's like if we have more electrons here and we have a bigger flow rate, we get more power. Why do we need volts and amps involved? Can't we just have amps and just go, what if we just increase the current? Means we'll get more power because we'll be getting more electrons to where we want them to go. But if there's not that reservoir of electrons at the start, it doesn't matter how much current you don't have the supply of electrons getting into your conductor. So you might have the widest river in the world, but if you don't have a lot of water upstream, you're not going to get a lot of water flowing down that river. So volts, let's call it a reservoir of electrons. Current is the flow rate that those electrons can move. Combine those together, you get the overall power. And let's say power is our ability to get electrons to do work. Apply a force over a distance. So the more power we have, the more work we can do. The less power we have, the less work we can do. If you have a high-powered amp in your stereo, you can get more electrons to your speaker, which means you can make more sound. If you've got a weaker amplifier, you don't get that number of electrons to your speaker, which means they're not going to be as loud. It's all the same thing. Speaker cable is rated in AWG. And there's an AWG table in the notes, American wire gauge. And pretty much the lower the number, the thicker the wire. In basic terms, but really the lower the number, the more current that they can handle. So the more electrons they can allow passing through them over a given amount of time. And really they do that by decreasing the resistance. So the lower the resistance, the more current they allow going through there. And with wire, generally speaking, if you have two wires of the same material, but one's thicker than the other, the thicker one will have less resistance and will allow more current. So that's what watts are. Watts is work over time. And we measure it in joules per second. A kilowatt is just equals 1,000 watts. So if we say something is rated at 1.5 kilowatts, that means it uses 1,500 joules per second. So if you think about that hopper, 1.5 kilowatts, and running it for 5 minutes is 1,500 joules So 1500 joules per second, 1500 joules times 60 seconds in a minute times 5 minutes. So that's a lot of joules of energy being used by that appliance. So this is how, in the beginning of this subject, what we do is we go from basic discussion about what joules are and work, and then we start bringing it into terms which we can apply within in the practical workspace. And that's generally in terms of power. And that's what topic 2 is all about. More than a person moving all those boxes of grapes. So what we do in topic 2 is we introduce this concept of power and watts, so electricity. Then in topic 3, we start talking about the efficiency of electricity, where energy is lost when we're converting electricity into, say, movement, and how that is related to pumps. And again, a lot of the examples are in a winery, but equally as applicable, exactly the same application as using pumps in a vineyard, using pumps in an aquaculture centre, using pumps anywhere, using pumps to move crude oil. It's all the same. So we quickly ramp up from this real basic conversation in tutorial 1 up to real application of that in topic 3. And I think even with our example, moving the boxes into the bin, we saw how we can, with this rudimentary knowledge, actually start modelling activities in whatever industrial setting or agricultural setting we're using it. A great example in topic 1, where we can move this very rudimentary understanding through to more complex principles, is the discussion of things like conveyor belts with rollers. And we talk about how rollers reduce friction. So if you're bottling something in a bottling line, you'll notice that a lot of the time, say the cases move on rollers. And you can push a box of wine or a box of anything along a conveyor belt of rollers really easily. You just push it with a couple of fingers. Whereas if you were pushing that along the concrete, you wouldn't move that box very far at all. That's because the rollers are reducing that friction. So we need to apply less force to get that mass over distance. And with our understanding now, we can actually model that and go, okay, if I invest in these rollers, this will reduce the friction this much, and this will reduce the energy input by this much. But if I was getting a worker to pick up a box and move it 5 meters and place it down, how many joules would that require compared to if I bought a conveyor belt and got the boxes to move along that conveyor belt? How many joules of energy would be required in that? And how much does it cost me to get that many joules of energy from humans compared to how much it will cost me for that conveyor belt? So even when we're just building up the principles at the start of this subject, we can really start applying in some really interesting ways. And that's what really excites me about this subject, to be honest. So, what I'd like you to do is go through that case study yourself after reading topic 1 and topic 2 and knowing all those calculations yourself. It's a very simple example, but please go through it. There's an example in topic 1 which asks you to calculate the amount of force required or work required to push something uphill or drag something at an angle. And you'll see that the calculations are a little bit more complicated, but not very much at all. So go through those, please. But alert, the 8th of August, which is exactly 1 week from today, tutorial task 1 is due. That is the construction of your winery or aquaculture centre. All that has to be is a simple building with 4 walls and a floor and 2 tanks. And those 2 tanks, remember, have to be individual units. They can't just be pulled up off the ground. So please go through, and that all makes sense if you've gone through the Google SketchUp tutorials. So please do that. Feel free to send me through your work in progress, or if you think you've done it but you haven't nailed it, you're not sure if you've nailed it, just send it through and I'll tell you. But don't forget, if you haven't listened to tutorial 1 recording, don't forget the submission minimum standards, which are found at the bottom of the assessment, the list of assessments. So even this simple task of creating a winery, I want you to present in the proper fashion with a heading. Just make it look, I just want you to make it look nice. Make it look nice for me. So from next week onwards, also what I'm posting up is the specifications for the Toyota electric forklift. I want you to have a look at that spec sheet and look at the battery storage, which is the number of, they measure the number of amp hours, and the amount of energy used to drive it, to work out the time, the dry time you get from the battery. Give that a go yourself during the week, and we'll discuss that at the start of next week's tutorial. But leisurely, please go through topic 1 and topic 2. Have a look at topic 3 if you wish before next week, and do tutorial task 2. Does anyone have any questions about that at this point? I really appreciate you guys coming on. I'm going to put the recording up. If you missed the first bit, yeah, well, of course he would. Well, just tell him yes. Tell him yes, but then no one will actually do it, which will be hilarious in its own way. But it's fun. I'll tell you, once you start building your winery, it is addictive fun. If you haven't viewed the first tube, I put up all the ones that they did a couple of years ago, and they're just absolutely awesome. And they absolutely love doing it. So get stuck in. It's awesome. All right, thanks guys. It's just bloody great having you on. And next week, I want to hear a little briefly about what everyone's up to at the start of the tube. That'd be awesome. So 7 o'clock start next week.